Started. Thanks everyone and welcome to the Kotak AI Center talk. And thanks for showing up on Monday morning. I know it's a little challenging, but it's like a great pleasure to have Mohit with us today. So he's a very distinguished computer scientist, faculty member at University of North Carolina. He received his PhD from UC Berkeley. Before that, he was an undergrad at IIT Kanpur. Yes, yeah. Okay. Yeah, I'll not repeat all of that again. Yeah. And then he's been doing exemplary work, lots of seminal work in multimodal learning. I mean, right now multimodal learning is very popular, but I guess he was the hipster in the area. Started working on that before it was cool. And yeah, lots of recognition and awards along the way, including awards from DARPA and most recently the IIT Kanpur Young Alumnus Award, and lots of best paper awards from top conferences like ACL and all. So it's a great pleasure to have him here, and he's going to tell us more about multimodal generative LLMs. So, yeah, over to you.
Great. Can everyone hear me?
Yeah.
Great. Thanks, Partha and Danish, for hosting me and for the kind introduction. And yeah, I completely agree about Monday mornings. I'm definitely not a morning person, but now I have to be because of the baby. So thanks for coming. So like Partha said, I'll talk today about a lot of our journey for multimodality, which now you hear a lot around you. We were doing this, I guess, since the last at least maybe 11 to 12 years. And so I'll be able to hopefully show you a journey of how we got from some of the early and the first multimodal BERT kind of models to very latest generative models that can do any-to-any generation. And very briefly at the end, my group is pretty big. It's around maybe 18 to 20 PhD students and postdocs. So we also do a lot of work on non-multimodal things like explainability and model editing, or faithfulness and factuality in generation. A lot of new recent work on efficiency, model merging, and so on. So I'll try to give brief glimpses, or just for people's interest, right, in case you're working on that at the very end for offline conversations. So let me get started. So like I said, this will be a journey of multimodal generative LLMs, and I'll focus on three aspects. One is their unification. So think of it as unified or universal multimodal learning models, such that you can improve their generalizability, have shared knowledge, and help each other, and be more efficient. Then the second part will be about interpretable multimodal generation. Specifically, can we use the power of large language models and their capabilities in programming and planning to do very different and complex kinds of multimodal generation tasks, all the way to even long multi-scene videos. And then lastly, but not the least, in fact, one of the most important aspects is also evaluation. Right, text generation itself is so hard to evaluate. I'm sure most people in the room already are aware of this. So multimodal generation is even more new and more challenging. So we'll discuss a little bit of evaluation of fine-grained skills, faithfulness, social biases, etc. And then I'll end with some conclusions and next big challenges. So let's get started on the first part. So just to give you a little bit of brief history here, which I think this room doesn't really need, but you've all heard of the pre-training and then fine-tuning paradigm, right? At this point, I mean, it's a bit all over the place and all around us right now. So the motivation of this back when it started, right, was that the amount of data is very limited in the downstream tasks that we are trying to work on. So pre-training gives us a way to enable much more supervision, right? Natural supervision is what you could call it, right? So in the vision world, you could do this through things like ImageNet, and then have a pre-trained model like DenseNet, and then you would fine-tune tasks like object detection to get faster RCNN kind of models. Or in language, you would have things like Wikipedia, and then do a masked language modeling kind of task, which I also call a fill-in-the-blank task, right? So basically, you just take sentences in Wikipedia, remove a word, and ask the model to predict the missing words in context. So think of it like a fill-in-the-blank task, right? So you would also do pre-training on the language side in this way, build pre-trained models like transformers, which then you could fine-tune on downstream tasks like sentiment analysis or others. So that's basically bringing us to the limitations of how, if you were only pre-training single modality tasks, right? The limitation, as mentioned on the slide, becomes that these single modality pre-trained models are not aware of the interactions between the vision side and the language side, right? Early useful work tried to do things like late fusion, right, or multimodal fusion layers, where you could take these pre-trained models trained separately on vision versus language, and then add some late fusion layers, right, to try to come up with some interactions between them. And then you would apply these sort of late fused or combine these models, right, as a post-processing, and then apply these to visual question answering or navigation or grounding kinds of tasks. But obviously that's not ideal, right? So you would want a pre-trained model that understands vision and language from scratch. So this was the first pre-trained multimodal kind of BERT model, which we call LexMERT, right? Large-scale cross-modal pre-training. And the idea here is very simple. Right, you would basically have at the bottom the usual language encoder with masked image modeling or fill in the blank. And on the image side, right, you would also do things like masked image modeling. So think of it as a fill in the blank task, but for images, right? You can take out patches of an image and ask the model to regenerate or reconstruct or repredict, reimagine that patch, right, given the rest of the image. So that basically could be done to get an object relational encoder versus a language encoder. And then you would also have this third new encoder called a cross-modality encoder, which would get its own pre-training tasks. And these pre-training tasks will be multimodal. So it could be things like multimodal fill in the blank, where what I mean by that is fill in the blank on the language side, but also given the image, or fill in the blank in the image side, but also given the language. Or you could have a lot of natural supervision, or at least more easily available supervision, like matching images and captions, right? So positive and negative pairs. So that becomes another pre-training sort of task. Or you could also go all the way to visual question answering and other kinds of cross-modal pre-training tasks. So this is not the focus of this talk, right? This is just some history where, like BERT, this also, right, as the first multimodal BERT model, achieved very big gains and state-of-the-art on several vision and language tasks, like VQA, grounded QA from Stanford, NLVR2, WizWiz, and so on. But coming back to the motivation of the unification part of the talk, since then, I think I'm not exaggerating if I say that there's more than 1,000 models that have come up, right, for all kinds of different multimodal pre-training models. And all of these have various different architectures, so they could differ in things like single stream for vision plus language together versus parallel multi-stream models, different kinds of attention methods, different kinds of objective functions, encoders, decoders, different output heads, different even specialized modules like OCR or ASR or tokenizers and so on. So that brings us to the motivation of the first part, right? When I say unified or universal multimodal learning, can we, I'll show you a progressively increasing unification from these 4 examples of how we can work towards building a truly sort of universal or unified model where you don't have specialized architectures and specialized pre-training for individual overfitting on individual different kinds of multimodal tasks, but can we instead have a unified single model that has shared pre-training objectives, shared encoders, shared parameters, shared knowledge, right? Also leading to a lot of free efficiency. So let's go through these 4 examples. So the very first one was the first unified model called VLT5, which we did in ICML 21. And the idea here was that coming back to this issue of very diverse vision and language tasks and their specialized models, right? So let's look at 4 examples. Visual question answering, right, takes an image and a question, and then the model has to generate an answer. Usually in VQA, it's a 2000 kind of classification vocabulary, right, where the model has to choose the best answer out of, say, 2000 possible answers. Or something like image captioning would instead have the image going through the model to generate a caption. Visual grounding is more interesting, where you're given an image and a very specific referring expression, and you have to actually ground the region, right, the sub-image or the region in the image that this referring expression refers to, right? So this is called visual grounding, visual pointing, referring expression comprehension, a lot of names for this task. And then another very different task could be multimodal machine translation, where given a language 1 and image as a bridge, you have to generate the second language, right? So the image is supposed to serve as a bridge here to give you additional context. right? So instead of going from language 1 to language 2 to language 3, where language 2 is the bridge, right? A lot of you also worked on translation, I assume. Here, the image would be the bridge. So now in red, I'm showing you some quick examples of all the specialized models, right, that have come up for these different kinds of tasks. And they're specialized in the way that I mentioned, that they're obviously trying to get right state of the art on that specific task. So they have overfitted the architecture to the special needs of this task in terms of the encoder style, the decoders, the output heads, the attention methods, right, the pre-training data, the pre-training objectives, all of that. So, I mean, just to give two simple examples, for something like visual question answering, the image and language question comes in, and it would go through a very specific vision language transformer one, and then it would have a VQA head, and then it would have a sigmoid, like I said, over top K answer scores out of the 2,000 different vocabularies, right, that VQA tasks have. So it would be multi-label classification. Whereas for something like visual grounding, you would have the referring expression and the image, and then it will go through another very different VL transformer, but then it would also have a different scoring head. In this case, it would be a region scoring head and a softmax instead of a sigmoid, and then it would classify the different score based on the different highest scoring regions. So the motivation of VLT5 was that can we tackle all these vision and language tasks with a single objective? And the answer is yes. In this case, we tackled it by treating everything as text generation. So the motivation here is that I'll give you some examples of how various tasks can be treated as text generation. So for example, if it's multimodal language modeling, right, the task is multimodal fill in the blanks. So a dash is a dash over a fire hydrant, and the answers are supposed to be man and jumping, right? So a man is jumping a fire hydrant. So obviously that can be handled as text generation, right, as I show on the right side here. Or it could be something like VQA. So the answer also could be generated piece by piece instead of classifying over 2,000 vocabulary items or question answer options. Then something like visual grounding is interesting, where instead of classifying different regions and scoring them, you could ask the model to actually generate the ID of that box, the correct box, as text, and in fact even the coordinates, the x1, x2, y1, y2 coordinates. And then obviously image text matching instead of a true false classification could also be treated as text generation. And there's 7-8 different tasks that could be done as text generation in the same way. This is the simple idea of VLT5, that everything is being treated as multimodal conditional language modeling. So the task prefix goes in, right? So this was an early example of task prompting. And then you would have the language side of the input. It could be a referring expression or a visual question answering question, or it could be right machine translation language 1. And then the last part of the input is the visual features. And then all of this would be fed through a very simple bidirectional multimodal encoder single stream. So all the vision and language features are in the same stream, and you just do bidirectional multimodal encoder. And then on the output side, you have an autoregressive text decoder, where you basically, for that task, as I showed, like you can basically start generating its output piece by piece. So this was the basic idea here. And like I said, in the top part, now you will see the specialized architectures in blue. And then in the bottom, I'm showing you how VLT5 can handle all of these with the same architecture and the same pre-training objectives. So visual question answering, I already showed you as the VQA head and the fire hydrant, but now it could just be generating the words part by part. And then for visual grounding, instead of scoring the regions, it can just generate the ID or the coordinates of the box. For something like NLVR2, this is also an interesting task. Think of it as a multi-image relationship understanding task. So you could have 3 images in the data set, and the task and the question is, do only 2 out of these 3 images have a red ball next to a yellow bottle, right? Something like that. So you have to do this sort of logical understanding about each image, but then also do sort of computations right across the images, that only 2 out of these 3 images have a certain property versus all 3, or only 1 of them, or none of them, right? So here also you could easily just extend it to feeding in the multiple image regions from the image side of the input, the NLVR question that's being asked, and then just generating true or false as language autoregressive decoder. And then lastly, for machine translation example also, right, you could just have the task prefix of translate language 1 to language 2, the language input, the image input, and then generate the second language. And here also you could do this sort of zero-shot transfer too, right? Because since you are feeding in the language names, you could also use the model to generate bridges that it has not seen before. right? If you've done L1 to L2 and L2 to L3, you could also ask it to do L1 to L3. So I'll not go into too much of the results in most of the talk because I'm covering a lot of material, but I mean, the papers are all out there and I'm also available for the rest of the day for chatting. But two main results here was that VLT5 compared to all the sort of specialized models on these 8 tasks, VQA, GQA, NLVR2, RefCoco, and so on, all the way to the multimodal machine translation dataset, without having any of these specialized architectures, gets pretty reasonable and comparable performance to all of these models. And more interestingly, since it's a joint architecture, you can also share the parameters. So instead of 7P parameters, you can just have P 14% of the parameters and still get similar performance. Other advantages in the paper you'll see is that it can also perform better on rare or unseen categories, right? Because it's a text generation model. So in VQA, there's these very challenging splits called unseen or rare category splits, right? Where it tries to test the model on labels that are outside the 2000 training vocabulary, right? So there, this will have an obvious advantage that since it's generating piece by piece, it will be able to handle rare and unseen categories much better. So since the last 3-4 years after VLT5, a lot of useful works on unification have built on top of it, right? So you probably played with SimVLM, Flamingo, OFA, Unified IO, some of these. So this is sort of the first level of unification that I wanted to talk about. Now, like I said, I'll sequentially progress with more and more unification and complain about the previous model, right? So the complaint you can have about the first model here is that, okay, it's great that it sort of combines the output side through text generation, but the input side, right, is still not unified because you still have a separate image encoder versus text encoder. So in TVLT, which we call textless vision language transformer, this was the NeurIPS 2022 oral. The idea here was, can we also combine the inputs, vision and language side, by treating everything as masked image modeling. So now we are going in the reverse direction. Like, let's treat everything as images on the input side instead of text. So the basic idea here was that we wanted to get rid of all the sort of annoying tokenizers and ASR and other issues. So we've done a lot of work on video and language modeling in the last 10 years. And one of the biggest issues there is that the alignment between the video frames and the ASR-based text right input is very misaligned. So the text subtitles and the video frames have a lot of noise and misalignment issues, as well as ASR and tokenizers, right, make the models very heavy and slow because videos are already very slow and heavy. So the idea here was, can we get rid of all the tokenizer and alignment and subtitle issues completely and directly work from the audio, right? So the idea would be that you treat everything, like I said, as image patches, right? So on the vision side for image frames, right, that come from the video, you're doing this fill in the blank task, like I already told you, right, for images. So you take out patches of the image and then ask the model to reconstruct that missing piece, right, based on the rest of the image. Now, we also show that you can do the same thing for audio spectrograms. So you can take the audio as spectrogram images, and then you can basically take out patches of the spectrogram and ask the model to reconstruct that part of the spectrogram given the rest of the image. So this allows you to have unified VIT, which is vision transformer style patch embeddings for both the video and the audio side, right? And then you have a masked autoencoder style encoder decoder. So the encoder now is allowed to be completely shared for vision and language because both of them are basically the same masked image modeling objective. And then the decoder parameters are also shared, but they reconstruct, right, the different audio and video images. So they are still different decoders, but with shared parameters. And the two objectives are the usual objectives. One is the masked autoencoding that I already told you about, the masked image, right, patch reconstruction. And then the other popular objective is usually contrastive learning, where you give it a lot of pairs of positive and negative video and audio, right? And the model has to differentiate between the positive and negative pairs. So again, I'll keep the results brief, but the results were pretty surprising to the community. Basically, the main surprising takeaway was that this audio-based textless vision language transformer, which does not use any text modules, right, can still perform very competitively with text-based models on different kinds of tasks like image retrieval, video retrieval, visual question answering. And in fact, it does even better than text models for things like multimodal sentiment analysis and emotion analysis, a lot of the CMU data sets. Because, right, it gets that additional free sort of signal when you need some emotion, pitch, right? Those kinds of features for sentiment and emotion understanding. But the best part is now you are 30 times faster and also only have 1/3 of the parameters. And here are some examples of what kinds of reconstructions the model can do on the image side versus the audio spectrogram side. Okay, so the next level of unification now, if I complain about the previous model, okay, we've combined things on the input side and the output side. But if you think a little bit more sort of practically or philosophically both ways, right? I mean, all these tasks and these models are very artificial in a way that we expect the real world to operate in a way that we have a very clean image and we have a very clean question and the model is given the image and the question, right? And then you ask it, okay, can you answer this question against this image, right? That's not how most of our real applications work. Real multimodality exists in a very sort of complex structure around us, right? It could be things like web pages or publications or utility bills, right? Or finance reports. So here all kinds of modalities are mixed in very, very diverse different ways. There's no sort of uniform structure across them. So some of the text will be available as captions, headers, footnotes, or it could be paragraphs, right? And then images could be general images or logos or signatures or plots or tables, right? So this brings us to the next paper, which was CVPR 2023 oral called UDOP, Universal Document Processing. So here the idea is that can we treat not just text and images as the same modality, but also layout, right? So I'll give you a motivation of why that's important. So it will take something like this kind of utility bill or any kind of publication or web page input. And so basically you're unifying, like I said, vision, text, and layout for universal document processing. So what it does is it unifies these three modalities, and it can do that now without any specialized modules like OCR, right? So OCR, optical character recognition, is another very painful sort of process for multimodal tasks because a lot of the OCR modules, right, are not available for a lot of domains or right, low resource domains and languages. So the idea of unification here also allows you to get rid of things like OCR, or in the previous example, get rid of things like ASR and tokenizers. And the main difference here is that what you want to do is now, so you have both the single modality tasks as well as mixed modality reconstruction tasks. So single modality would be the same thing, right? I would basically take out a part of the image. I would treat this whole thing as an image. I can take out this part and ask it to reconstruct that. Or text reconstruction is also similar, right? I'll take out a few words in the paragraph and ask the model to reconstruct that. But the new thing is that you also want to have mixed tasks reconstruction. So what I'll ask the model to do in this, for example, the orange example, is that don't just reconstruct the text, but reconstruct the text with its layout prediction. So this intuitively should basically mean that the model is learning not just what text was missing in this fill in the blank, but what kind of text it is, right? Because it also needs to predict the location or the layout of that text. So it will start learning that this kind of text usually sounds like a header or a footnote, or this kind of text usually appears in a caption, right? As a human, you'll be able to differentiate pretty easily. If I just give you random pieces of text from a paper, right, like a publication, you will be pretty good at predicting whether this is a footnote, right, or whether this is a caption of a figure or a caption of a table, right? So that's what we are teaching the model, that don't just reconstruct text as English understanding, but also understanding the layout of the document. So then it understands that, okay, I'm not just learning how to fill the missing part of a text, but also understanding whether this is a caption style language versus a footnote style language. And same thing for the image. We don't just ask it to reconstruct the image missing piece, but also jointly reconstruct or predict the layout, where it came from, right? Which position of the document or which location in the document did it come from? And that has the same advantage that now it understands that, okay, this is more like a logo at the top of a document, or this is more like a signature at the bottom of a document, or this is more like a certain part of a plot, right? So it's basically the simple idea that you want to be able to. So there's two advantages here. One is you are able to unify all the three modalities into a single encoder. And the second thing is now it allows you to do these mixed modality reconstruction tasks. So yeah, that's pretty much, again, I like to have papers simplified into 1 or 2 slides. So that's the main takeaway here, that you are able to combine all the three modalities, do mixed modality tasks. And the other big advantage here is that we are not just asking so let me give you a brief summary of the results first. So there's a popular benchmark called Document Understanding Benchmark, DU, and it has very interesting 8 or 9 tasks on all the way from things like document visual question answering, where instead of, like I said, giving you a very clean single image and asking a question against it, you're given a whole document. It could be a publication, it could be a finance report, it could be a utility bill, it could be a website, and you have to answer questions in the wild on any part of the documents. It has things like table NLI, right? Entailment for tables, table question answering, document information extraction. So very diverse tasks. So UDOP got the rank 1 on I think 8 of the 9 tasks and state of the art overall. And the data set is very useful, so I would recommend you to try it. It has very diverse domains, like I said, finance reports, papers, websites, papers from things like PubMed and some part of archive. And the other big sort of technical novelty here was that it's so this is if I just had an encoder based model, right, it can only go so far. So the best way this model was able to do state of the art is that it's also learning how to not just understand the document but be able to do very fine grained edits or generation based edits in the document. So in fact I can ask it to add text I can just give it a box and say add text here, right? And because of its mixed pre-training objectives, it can understand that this kind of layout or position has this kind of text, right? Because we taught it to predict text and layout jointly. Or I can ask it to replace text, right? So it can basically maintain the exact same style and the print and all the format of the document, but basically be able to do very fine-grained edits, right? It could do these different kinds of the serial numbers, signatures, logos, right, in the same exact printer ink and so on. And for that reason, you can understand that we also didn't release this decoder because the point, it can have a lot of misuses, right? So the point of this kind of capability was to make the understanding of the model much stronger through generative editing, as opposed to have a standalone decoder that can do that. Yeah.
So here, are the layouts pre-decided and fixed in number?
No.
So they can be any real values?
Yeah, exactly.
Okay.
So that's why the data set is very useful. Like it actually has, I mean, you can imagine, I don't know how many companies you've changed for utility bills, but I've done a lot of changes in the US, and every bill looks completely different from each other, right? And then most websites look completely different from.
No. My question was like, for the layouts,
right?
Are there like fixed sets that the layouts could only be like 8 in number? Like,
oh no, it's all real numbers.
Real
yeah.
Okay. Awesome.
Yeah, very fine grained. So that's why, I mean, otherwise it would be very hard to be able to do like serial numbers that are rotated 90 degrees. So it can handle all continuous spectrums on all 3 axes. I mean, all 2 axes, but you're also rotating. Okay, so then this brings us to the last part of the unification side. So now if I complain about all the unification we've done so far, the thing that's still missing for true unification, right, or universal models, is that none of these models can handle unseen scenarios of modality combinations, right? If you're training a model for, say, image plus text to audio, right, can it handle image plus text to video? No, right? You've never seen such a model, I'm assuming, before. Or if it's been trained for image to video, can it also do image to video plus audio, right? So this is the idea of CODI, which was presented last month at NeurIPS. It's called any-to-any multimodal generation through composable diffusion. So the idea is without being able to, without getting into the exponentiality of these unseen combinations, just with a linear number of objectives, can we handle unseen scenarios of multimodal combinations. So let me give you a demo first. So like I said, this CODI can jointly generate any-to-any combinations from video, image, audio, and text via composable diffusion. Let's look at some examples. So this could be things that you give it to the model as inputs. I can give it an image. This looks like Times Square, right? A busy street. I could give it a sentence saying teddy bear on a skateboard. We avoid generating people, right? So we're mostly working with non-human faces. And we could also give it an audio clip, say rain ambience, right? And then what I can say to CODI is, hey, it can basically take any things on the input side and generate any things on the output side, any combinations. So I could ask it, hey, take this yellow line with telling CODI, take this rain ambience audio. So I maybe should Is the volume full? I think it's a little bit low. Maybe. Can people hear the audio? Okay, great. Thanks. So yeah, so basically I can ask it to do audio to text, right? So it takes this audio clip and it can generate some description, right? Raining, rain, moderate. Or I can say, take these two red things, which is the image and the audio clip, and give me, let's say, another audio. So now what will happen is, one second. So basically, it will take the rain audio and the image, and automatically from the image, it will understand that it's a street image. So it will start generating street noise, right, combined with the raining sound. Or I can go more complex. I can say, take all the. Yeah, this is always a bit tricky. Take all these three things. So now I can say, take all these three purple things, the image, the text, and the audio, and let's say, generate me an image and a text, right? So now, I don't know how well you can see this, but basically it's taken the same Times Square background, put the teddy bear on a skateboard because of the text, and made the floor wet, right? Because the audio clip had rain in it. Or I could say generate, the most maybe complex example could be also take all these three things and generate a video plus audio. Right, so the thing you see here is that you obviously again see, right? So you obviously see the Times Square thing in the background. Now you have moving cars and stuff. You have more dynamic rain because it's a video. You see the teddy bear coming on a skateboard, but the most interesting thing is you hear three audios. So let me play it one last time. Right, so it's the rain sound, which was obviously already in the audio clip, but the street noise because of the image being a street image. And third of all, you hear the clicking sound of the skateboard, right? Because the sentence said skateboard. And you can check the more high quality audio on the website. So now let's get into the technical side of it, right? So like I said, this Cody any-to-any multimodal generation is sort of the first generative AI model that can handle any combination of input modalities to generate any combination of output modalities. So this obviously has a lot of interesting use cases, like being able to have your own many modal, right, storyboards where people have different inputs of images, audios, clips, audio clips and stuff. And you can basically mix and match and ask the model to generate stories for you. But on the technical side, right, like I said, training these kinds of models has very significant costs because the number of combinations scales exponentially. And most importantly, the training data is missing for a lot of these modalities. So that's what Cody can do, right, very effectively. That can be it can basically efficiently do all these missing combinations without relying on seeing training data for every possible combination, as well as only doing it through a linear number of objectives by doing this basic idea called bridge alignment, right? So let me give you a very brief overview and then we can discuss more offline. It has two main stages. One is composable conditioning, and then the flip side is the joint generation, right? So the stage one composable conditioning allows it to take any combinations of input modalities to generate an output modality. So first you train a latent diffusion model for each modality. So Cody basically treats every modality as diffusion, right? As opposed to some of the previous models we saw, which was treating everything as autoregressive. Here, even text is being treated as diffusion. So this is an interesting debate, right, in the future of like whether everything should be diffusion models or autoregressive. It doesn't matter. It will be a third model probably, right? But the idea is, to me, the most important part is, can we handle unseen things without expecting academics and non-big companies to be able to pre-train everything from scratch every time we need a new situation, right? So composability is what we should focus on. The individual sort of models will keep changing. It should be basically a library of models, right? And some of them could be autoregressive, some could be diffusion, and these keep updating. But the combination capability is what needs to get richer. So the best part, like I said, is that first you want to train these independently, right, or pick them up from a library, right, just the state-of-the-art models that exist, such that you can ensure high-quality generation for each modality. And then for conditional generation, for example, if you're trying to do audio plus language to image, the input modalities are projected into a shared feature space, and then the output, so audio plus language, right, will get projected into the shared feature space, and then the output modality image, right, the LDM for that will attend to this, will extract its attention, right, from this shared space. So this allows you to basically combine anything on the input side, and then on the output side, it's similar. You take a you first add a cross attention module to each LDM, and then there's an environment encoder which allows the LDM latent variables to get projected into a shared mixing space. So this environment encoder allows you to mix the latent variables of all these LDMs on the output side, such that you can do video plus audio or different kinds of mixing that you've not seen before. So that allows the flip side of being able to mix or generate any group of output modalities without having trained on these combinations. So a few more examples. If I had audio plus image and I asked the model to do text plus image, I can give it an image and this piano audio clip. And then, since I said generate a text plus image, it will try to take the same forest ambience and put a piano player inside that. I could say text plus image, take this text sentence and this image of a panda eating bamboo, and I could ask it to generate a video for me. So it will try to have the same again, combine the information from these two models. And then fresh, sort of hot off the press, is the last piece, sort of missing piece in this universality, is that you could still complain something about Code 1 that this is not a natural way to talk to a model, right? Text plus image to video, or like these 3 purple arrows going to 2 purple arrows, right? So ideally, the last missing piece should be that you should be allowed to talk to this model and have a conversation with it interactively, as well as you should be able to mix, interleave, right? That's the other missing piece. These prompts should not just be single modality. Even on the input and output side, each single prompt itself should be allowed to have mix of modalities, right? Audio plus image in a single sentence. So this is what the sort of Code 2 from like a few weeks ago sort of completes, right? The idea here is in context, interleaved, and interactive. These are the 3 I's that we added. So let me give you an example briefly. So I could say learn the subject in image 1 and generate with it on the concept represented by these sets of images, right? So what it will do is it will basically take the dog and then put it in this kind of circular archway garden, right? Because that's what we said to generate with the second concept of images. Then, like I said, it's interactive. So this is the interleaved part, right? That in the single prompt itself, you could have multiple sets of images, but I'll also show that you can have modalities mixed in. And then the interactive part is that I can continue the conversation. So now I can say edit this image in the vibe of and give it an audio clip, which in this case plays a rain sound. So now it will generate the same image with the wet floor and a misty kind of rain ambience. And then I could continue the conversation. I can say, now what's the edit between these 2 images, and then apply it to the image, right, that we are working with, and tell us what the effect is. So it can do some sort of like these subtractions, right, and analogies, where the edit between these 2 images is the change of season, right? It's going from summer to fall. So it will basically take that same image, convert it to fall leaves, and then also explain to you that I changed the season of the scene. So this is just the high-level example, and then in the paper you'll see Code 2 has a lot of versatile abilities. It can do exemplar learning. We apply a new concept to A and got B. Now apply the same concept to C and give D, right? So all these analogies that you probably remember from NLP analogy papers, right? A to B and then C to D. It can also do things like A minus B plus C, right? So we overlaid a new sound to street noise and got street noise plus raining. Now apply this same sound to train noise. And so then it should generate train noise plus raining. So I mean, these are not given to the model, right? These are obviously audio descriptions that I'm just showing you in case the audio is not very clear. So A minus B plus C, right, to give you the final output. It can also, so this is exemplar learning. It can also do reasoning. Given X, Y, and Z, what happens next, right? So keep reducing blocks one by one, multimodal generation with reasoning, right? So given these video frames, what will happen next? So basically generate a sound and image for it. It could also do subject-driven video generation. Given a set of pictures of my cat or my neighbor's cat, generate a video of this cat. It can do composition, right? A on B, so boat on a certain kind of water like ambience, concept learning, and so on. So this basically is very hot off the press. So Cody 2 is sort of, think of it as Cody 1, like I said, with interleaved prompt capabilities, as well as being able to talk to it through multi-step interaction. So this brings me to the end of the first part of the talk. The second two parts are shorter, around maybe 10 minutes each. So any quick questions before I move to the second part? Yeah.
In the coding model, how are you using to like keep an encoding of the past, let's say whatever interaction you have had earlier? So what is the shared state that is maintained?
So it's the shared space is basically it's using a multimodal language model to maintain all the history. Yeah, I was not able to show the actual model figure for this because this I just added sort of as a demo. But yeah, so if you see the paper, it basically uses MLLM, right, multimodal language model as a backbone, such that it can basically maintain both the language, audio, video, or image, right, all the multimodal history, and then it can also attend to it and choose if it needs something to go back to the previous conversation, or does it only need the previous outputs. Okay, I'll take more maybe questions towards the end. So then let me move to the second part. So this is, like I said, this is a little bit on the interpretability side, right? So now let's move on to the discussion of whether we can use the power of large language models, right? So large language models are really good at being able to do a lot of planning and programming, right? As you've probably seen a lot of examples around you. So can we use that power to be able to do interpretable multimodal generation, and for three aspects. One is for better understanding, right, through interpretability of what the model is doing, but not just for your understanding, but also the model's understanding. There's some recent papers that have shown, right, that generative models actually don't even understand themselves what they're generating. But if you do it this way, you'll see that the model actually is forced to be able to understand and tell you why it generated something. Second is control, right? It will allow you a lot of human in the loop control to be able to fix the generated images or videos. As opposed to just keep trying thousands of prompts, right, till you get lucky, or prompt engineering. And third is faithfulness, right, to errors. Like you will know which parts of the prompt it was faithful to versus not. So I'll mostly focus on the first two examples here. So VP Gen is basically, think of it as visual programming for image generation. And then video director is a more complex multi-scene consistent video generation example. And then I'll very briefly mention an education application of diagram generation. And like I said, the middle part, the blue boxes is what's the interesting part here. The LLM is being used to generate very fine-grained plans that go all the way from 2D bounding box layouts to multi-scene descriptions to consistency, co-reference groupings, and so on. So just to give you some background of the need for these kinds of interpretable LLM-based planning models, text-to-image generation currently, right, is mostly through black box models. So you can say two Pikachus on a table, or truck is behind a motorcycle, right? These are obviously toy examples. So if you feed it through DALL-E 1, 2, 3, or Imagine, or Stable Diffusion, all these different versions, first of all, you'll be very impressed by the visual quality, right? But then very quickly you'll realize that there's a lot of important semantic issues, right? There'll be obviously things like counting and scale and spatial relationship kinds of errors. So basically, there'll be a lack of fine-grained layout planning or control. There'll also be, like I said, a lack of interpretability behind the generation process, both for humans, but also for the model itself. And this obviously leads to a lot of faithfulness issues, right? So both false positives and false negatives. Hallucination means that it's generating something that I did not ask for, but also the reverse, right? It will miss things that I asked for. So the idea of using LLMs sort of programming or planning power to be able to do image or video generation comes from a more older field of neural modular networks, right? So visual programming is more like a new term, but this goes all the way back to even papers that were using neural modular networks for visual question answering, like Andreas et al. We did it for referring expressions called MATNet. We also had the first paper on programs for summary generation called summarization programs. And there's a lot of work recently on visual programming for image understanding called VisProg and ViperGPT. Right, so the basic idea is always the same. You have a bunch of modules that you've defined for different capabilities, and the LLM's job is to actually generate a program over these modules. And then you execute that program, and then the task, right, gets executed. But most of this work has been for understanding tasks, right, not for generation tasks. So VP-Gen is sort of the first paper that tries to do visual programming for step-by-step controllable text-to-image generation. And the way it works, I'll give you a very simple illustration of that, is that first you'll have something, again, this is a toy example, but if you have two Pikachus on a table, the first job that you will teach the language model is through in-context learning, right, is that given this caption, determine the objects and their counts, right? So two Pikachus on a table should output Pikachu 2 and table 1. Then the second job or the second step would be layout generation. So now I'll tell the model, the language model, given this image caption and the objects that you predicted, determine the coordinates of the objects. So this is the more interesting part, right? We are asking the language model to predict the bounding boxes of everything in the image. And the reason it's able to do well on this or learn how to do this well is that it's also using language information like to and on, right? So it will basically learn that the table's box average y coordinate should be lower than the y coordinates of the two Pikachu boxes, right? Because there is a preposition relation called on, right? Versus behind, versus left, versus right, right? So I'll show you some examples. And then finally, the third step would be once you have generated these boxes, visualized layout, now you will do something called infilling, where you'll basically take these boxes, right? And then use some image layout to image infilling model, like say Glygen, right? To be able to fill in the objects inside those image boxes. So very briefly in terms of results, what VP-Gen, so if you look at stable diffusion kinds of models, they are really bad at things like counting, spatial, or scale, right? So you get huge gains on these kinds of more semantic, fine-grained. So we'll discuss evaluation in the last part of the talk, but basically this is all issues that most models have not studied, right? You only look at things like visual quality, which is FID, right? Which basically means nothing. I mean, it's like the image looks good, but it's not measuring anything whether the content of the image is correct or not, right? So if you start measuring very fine-grained skills like counting, spatial relations, scale, you will see that these models are pretty bad. And so things like VP-Gen, which we just showed, right, through layout-based control, gives you very big gains on counting, spatial relations, size comparison. So here's some examples, right? If I say 3 boards, stable diffusion will generate a very nice, right, image, but it has nothing to do with 3 boards, right? It's just like maybe 50 boards, right? Because it's trying to minimize the FID with the training distribution. Whereas in VP-Gen, you can first make sure that there is 3 board boxes, right? And then you infill those boards. Same thing for a truck behind a motorcycle. You might generate the wrong sort of relationship with stable diffusion. But here you're already making sure that the motorcycle relationship of the box has a relationship of front, or right, with respect to the truck, because of the bounding box layout prediction that we taught the model. And the last one is even more interesting. A remote that is bigger than a cat is something that no training image has shown before. So it's able to handle very out of domain or out of distribution things, where it will make sure that the remote's box, right, is bigger than the cat box. So these are the basic sort of advantages, right? Like I said, since you're generating the layout first, you first have better understanding and planning of these relationships in the image. But the best part is it also allows you explicit control over these properties. If you still don't like the size of the remote, you could drag this box to make it bigger and ask the model to regenerate the image, right? So it can have interpretable correction of these unfaithful parts. I'll show you more human in the loop in the next example. So this is the more complex example of this called Video Director GPT, consistent multi-scene video generation via LLM guided planning. So most video generation models you've seen, probably all video generation models you've seen so far are single scene, right? So they basically will take an image and add some motion to it, right? But this is still a very open-ended sort of holy grail kind of challenge, like in this community, where can we have multi-scene long video generation? Because first of all, consistency becomes a big issue across those scenes, right? All the characters have to stay the same, but also the very fine-grained layout becomes more challenging because single scene has very limited actions going on, right? But if you have a multi-scene story, you also need to make sure that all the layouts and the actions look correct. So this is the first paper that tries to do it, called Video Director GPT. And the idea here is that, again, we have, like I said, 2 parts. One is the video planner, where something like a GPT-4 style language model will first try to give you the whole plan of this long video, all the way from individual scene descriptions to the entities, their names, their layout boxes, the backgrounds of each scene, as well as the consistency groupings, which you can think of it as co-reference in the NLP community, right? So let's get into the details. So this is another toy example, but I'll show you real examples in a bit. So just to fit it on illustration. So let's say a hungry cat is finding food, right? So what the first video planner stage will do, this is the video planner stage in blue, is that it will first try to predict all the individual sub-scenes of making this long video of a hungry cat is finding food. So first it will decide, okay, the first scene should be something like a cat is lying down on a bed, and it will also predict all the entities needed as well as their boxes, right? Color coded in the sense that all the boxes that have the same color are the same entity. So it's predicting the Siamese cat, and then since it's lying down on a bed, again, it's making sure that the x coordinate, right, of the box of the cat is longer than the y coordinate because it's lying down. And then the next scene, it can maybe predict that the cat gets up, right? So then the entities still stay the same. There's still a cat and a bed only, but the boxes change, right? So now the x coordinate of the cat becomes shorter and the y coordinate becomes longer because the cat has gotten up. So the language model is learning this through the different prepositions, and it's also predicting all the backgrounds, right? That in this kind of scene, this is probably a bedroom kind of background. And then lastly, the model will say, okay, now she goes to the kitchen and eats a snack. So a new entity comes in, and then the background changes to a kitchen. So the cat entity stays the same with orange color, right? So this is what the co-reference groupings are. The model is also deciding that, if you remember co-reference clusters, right? The way we used to do it when I was a grad student, the models would basically predict every time a new entity comes in, a pronoun like he or she or they, right? The model has to predict whether, or a common noun, right? Also, the model has to predict whether this new mention goes into an existing co-reference cluster, or do I need to start a new cluster, right, for a new entity? So it's doing the same thing now, but for video generation, right? This can all be done also for long text generation, by the way, right? These are very basic kinds of general frameworks. So we are also doing this for long text generation. So the idea is that it's predicting the scenes, the entities, their names, their layout boxes, as well as the color-coded co-reference groups, and then the background. And then the second part is where the vision side comes in. So the video takes all of this information, collects all these boxes, the background boxes, the entity boxes, and then it takes something like a single scene video generation model with spatial temporal blocks, you could use any single scene video generation model. And then what layout to vid, which is our module, does is it inserts these guided 2D attention modules inside these spatial temporal blocks, which allows you to do more layout control, right? So it basically, the best part here is very efficient. It can only update these guided 2D attention layout modules. Everything else can be frozen. And also parameters are shared across all the consistency boxes, right, in each frame. Everything that's consistent shares parameters. So all of this is done on only 8 A6000 GPUs or 4 A100s, which is unheard of, right, in the video generation community. So to give you some examples, what Video Director GPT can do is, one capability it has is multi-sentence to multi-scene. So it can have a very multi-scene description given to you, right? And a very unseen kind of scenario, which basically no training video has, right? A mouse is holding a book and makes a happy face, pulling petals of the flower, holding flower by his right paw. So you will see that the left side baseline models, right, cannot handle most of this because there's no consistency, right? These are all single scene videos. On the right side, you'll see the consistency of the mouse is very strong, but also the layout control is very strong, right? You'll actually see it holding the petals and like the flower in the right paw and then reading a book, right? So it actually is able to, because of the box generation first, it's able to have the book and then ripping the petals, and you'll see that in one frame, you'll see that the flower is in the right paw. Another capability it has is single sentence to multi-scene. Instead of giving it the whole story, you can just give it a single sentence saying, make a strawberry surprise. And then the model will first generate all the sub-scene descriptions and then repeat the same process. But again, with the consistency of the person involved, as well as the kitchen background and the objects. It also does very basic things that current video generation models cannot do, right? It's actually, you'll be surprised that current video generation models are still very bad at even basic things like direction control. Saying something like pushing a stuffed animal from left to right is very hard for current models. But because of the layout control and the consistency checks, right, the video director model can handle direction control much better. It can have human in the loop editing, like I said, right? So since we are first generating the layout, what you can do is you can actually generate the video first, And then if you don't like something, right, you can say, okay, I want to make the box of the horse smaller. You can just drag the box, make it smaller, and regenerate the video. Or you can say, instead of this background, I want a grassland background. So you can just add a grassland background box, and it can generate the same horse in a grassland background or a night street, right? So that's sort of the best part of these kinds of planning-based models, because the future is not, right, like these kinds of models replacing humans, right? It's all about sort of assistants to artists or humans or educators, right? We are working a lot with classroom educators through a NSF AI Institute. So this allows you a lot of fine-grained control instead of just let me get lucky with thousands of prompt engineering solutions. And the last capability I'll show is that it can also have input image given by the user. So you can give it your favorite pet cat and ask it to generate a story about getting up from a bed, going to the kitchen and eating a snack, and then sitting on a big window. Or I can just replace it with my favorite stuffed animal and generate the same story, right? So again, storyboarding video generation, but through your own image inputs. So half the paper is actually a lot of effort on metrics and data sets for this task. It's a very brand new task. So we've created a lot of work on how to measure their fine-grained skills like spatial, scale, count. Also, like I said, direction control, as well as their FID, FVD, consistency metrics we proposed, right, all the way to human evaluation. So hopefully, like this allows future work, right, to be consistent across metrics. And then the final example I'll show is Diagrammer GPT, which this is an education example. So it's kind of like VP Gen, but these are very, very different complex images. It's about diagrams showing very dense layouts and arrows and directions about, say, a diagram showing the Earth revolve around the sun 4 times, one of each solstice and equinox, right? So the difference is that these kinds of images have very dense layouts. They also need arrows and certain directions, as well as labels, right? So this would be sort of the pipeline where you would first generate GPT-4 or Vicuna. We show both open source and closed source. Models would generate the plan, right, through entity locations and entities, then visualize the plan, then infill to generate the initial diagram, and then add the text. And you could have human in the loop again here, where if the user doesn't like the first diagram, they could go back to the plan, edit it a bit, and then ask it to regenerate the diagram. So this is more for educators, right? Trying to explain very complex concepts to middle school students through automatic visualization. And then I can take 5 to 6 more minutes, right? Yeah. So yeah, so let's, I think we already covered a lot of the evaluation in the previous 2 sections. But very briefly, I'll also end with some of the evaluation challenges, right, in multimodal. I already showed you some challenges where measuring things like spatial or scale is very hard here. But I'll give you 2 brief examples. One is VP Eval is the evaluation version of VP Gen. Can we convert evaluation to a visual program first and then execute, right, the generated image against that program, but also get explainable errors of what part was wrong? And then DALI Eval, I'll discuss more of the social bias part. So I'll skip most of this background, but I think I already explained this background a few minutes ago, right? That before 2021, this is how generated images look like, right? So this is apparently some pasta, and then these are apparently 2 people playing video games, right? So we were pretty happy with these kinds of images. This is, in fact, from one of my students' older papers at AI2. So back then, it made sense to have metrics like inception score or FID, which basically just check the match between the training distribution of the images to the test image, right, the generated image. But then after DALI, right, I mean, FID has almost saturated, right? Lower is better, right, since you're measuring the distance between the distributions. So now images in 2021 onwards and DALI 2 and DALI 3 you've seen, right, started looking much better. So the quality of the image is already very good, right? That's not what we need to measure. Because, and that's what FID tells you, right, that it's already saturated to almost 0. But we have still a long way to go, right? Stack of 3 cubes versus social biases like NERS, right? A lot of these things are still long way to go and not being measured. So this is what the motivation for VP Eval was, that current sort of evaluation models that go beyond FID are just things like CLIP or BLIP, right? That just try to get you a random score between, I mean, not a random score, but a non sort of transparent score between the image and the text, right? How much do they match? But then you have no clue whether, like, how did this score get computed? What does this even mean, right? Like if one image has a score of 0.73, the other has 0.75, like what are the actual differences? They still might be very, very different in their capabilities or errors, but the numbers look the same. right? And then which parts of the image are actually wrong. If I want to improve my model in the next iteration, like what should I even focus on, right? Instead of just getting a 0.75, like what should I do with that? So visual programming for explainable T2I evaluation, VP eval, basically takes the prompt, first converts it to an evaluation program using neural modular networks, right, by calling different evaluation modules, and then it executes the program to not just tell you whether it's true or false, but also tell you which errors are true or false in the image, right? So these are some examples of the modules. It could have things like counting evaluation or spatial evaluation. If the target relation is right, then the x coordinate should be higher than the other x coordinate. If the target relation is bigger, then the area should be higher than the other area, right? So you first have a library of modules, as I already mentioned, and then you would basically, for singles, let me go directly to the multi-skill. So you could have a very long prompt like a white slope covers the background, while foreground features a grassy slope with several rams grazing and one measly and underdeveloped evergreen in the foreground. So you have to generate this very complex image. How do you evaluate it, right? So what VP eval will do is it will first convert this prompt to a bunch of evaluations, right? Object evaluation of RAM, object evaluation of evergreen, RAM should be greater than 1, and evergreen should be exactly equal to 1. And then the remaining things it can ask as VQA. What is in the foreground? The answer should be grassy slope. So the best part about VP eval is that it first gives you this sort of interpretable program, but then when you execute it, it also tells you which parts of the program were wrong versus right. So it will tell you that, okay, the first part is wrong, the presence of RAM is not found, the evergreen presence was true, but then the count of the evergreen is wrong because you asked for 1 evergreen, but there's 8, so it's hallucinating 7 extra evergreens. And then it can also say that the grassy slope part was correct, right? So it's actually telling you how did that 0.75 score come about, right? Which parts were wrong and right, and which parts do you need to focus on for the best next iteration of your model. And there's some metric human correlations in the paper, right? Whenever you propose a new metric, you have to measure human metric correlations and whether it gets better, right? Is your metric ranking outputs the same way as humans? And then there's another very recent paper with Google that we collaborated on called Davidsonian scene graph, which is about formal Davidsonian semantics. So this is a problem of VQA-based metrics, right? Where a lot of these metrics like TIFA, which some of you probably played with, convert the prompt to a bunch of questions, right? And then you check which of the questions got the correct answer. But the problem is that they have a lot of issues like they're complex non-atomic questions or invalid questions, right? Is there a red motorcycle is a bad question because, I mean, is there a motorcycle is yes, but it's not red, right? So that question is not atomic. Or it could be invalid question, right? If the motorcycle, is there a motorcycle is already no, then you shouldn't really be asking, right? Is the motorcycle red? But the model can still ask it and get an answer yes, and give you a score for it, right? You get some credit, but it's invalid. So you basically use a Davidsonian formal semantics graph here. Think of it like a directed acyclic graph that tries to make sure that the questions are basically connected to parent-child relationships in a way that the most higher level question, right, is there a motorcycle, has all these edges coming in. So if this becomes false, then you don't ask these child questions, right, about properties of the motorcycle. So this allows 4 things. One is we have ensured that every question is atomic, only asking a single piece of information. All of them are unique. You're not over asking, repeating the same questions to get extra credit. But you're also making sure of full semantic coverage. Every aspect of the prompt, right, is being covered in some question. So both false positive, right, and false negative issues. And lastly, most importantly, the valid dependencies. And then this is the last slide. So another third example of better metrics. So DALI eval was technically the first image evaluation paper that went beyond FID kind of thing. This was 2 years ago. We also did red teaming with DALI 2 OpenAI team and showed that bigger models were actually more biased than smaller models. So it's in their red teaming document. But the basic idea here was that if you have a lot of these prompts, right, like including accountant, decorator, dentist, designer, hundreds of options, if you ask the model to generate a person who works as a nurse, right, you will see a lot of bias here. So how do you measure it, right? So you can measure things like gender, skin tone, attributes, right, like jeans versus skirts, all of that, right? And the basic idea is that, suppose you take the example of skin tone. So this is known as monk skin color tone, right, 1 to 10. And the idea here would be that ideally a good model that's not biased, right, for these kinds of prompts should be generating a uniform distribution, right, over all color skin tones. So what you can do to measure is you can basically measure the bias by reversing that process. You can check for how skewed are the distributions, right? So that's basically the simple idea. You measure the average and the variance of the distribution, and that tells you how biased the model is. So some basic outcomes, more details are in the paper, but some interesting takeaways were that smaller models, right, like Mint-DALI, were less biased than bigger models like Carlo and Stable Diffusion. And then also some kinds of professions like engineer had much more skewedness or bias than some other kinds of professions like singer. So let me end here. So let me summarize what I talked about and some of the next big challenges. So I think one big takeaway here is sort of this debate about black box pre-training versus modular structure, right? So hopefully I convinced you that by bringing in modular structure and having plans over these modules, right, or programs, that's to me is the best balance, like using the power of large language models to focus on better programming and planning, right? Which modules to use, like think of it as a mixture of experts, right? Which modules to use, which experts to use, what importance to give them, also deciding when current experts are not enough and growing them or bringing in new experts, right? Whereas the actual experts, right, should be a library of modules where it could be LDM like diffusion models or autoregressive models, right? Things that exist and keep getting better, right, as new models come in. So I already showed you a lot of advantages of both interpretability understanding, but also more importantly, human in the loop control. And then there's a lot of other advantages, right? Like the fairness bias issue and the privacy issue of like being able to delete unwanted information and so on. We only covered 4 modalities, right, in this talk. There's many other modalities still much more important, in fact, right, especially for education applications, things like non-verbal modalities like gesture and gaze we are working on. One very important modality is action and interaction, right? We don't really learn just by sort of sitting statically, right? We dynamically learn by interacting with our environment. Like if you touch something hot, next time you know not to touch it, right? If you bang your head against the wall, right, you know not to do that next time. So the current challenge here is that all the simulated environments, right, it's a chicken and egg problem. If you put these models in a simulated environment, the simulated environment itself is built by us, right? So it's very limited capabilities that the model can learn because we are defining those capabilities, right? And if you put it in a real environment, then it's basically blocked by the capabilities of the current actual hardware robots, right? Because they are very expensive and they can do things very slowly and very few actions. So this is a very interesting and sort of next big challenge. Long distance video understanding and generation, I talked a little bit about. We've also done a lot of work on the understanding side, not just generation. And there's some big issues here to think about. We've shown some work where a lot of shortcuts might happen. You might be thinking that the model is actually doing long text or long video understanding, but it's actually just taking some shortcuts. A single frame is enough or a single sentence is enough. It's not really combining information as needed. So we have some work on counterfactuality to make sure that it's doing right for the right reasons. Fine-grained evaluation we talked about. This is another big thing. We're doing a lot of work on this now in our lab, and other labs are doing a lot of good work. But the idea of continual learning, but most importantly, unlearning, right? So can we basically figure out, first of all, where sensitive or unwanted or old or outdated or private information, right? All these kinds of unwanted scenarios are stored in a model, right? Especially it's very challenging if it's a black box pre-trained model. So which layers, which parameters exactly store that knowledge, and then can we edit based on that localized information? Turns out it's not that easy. So we had a NeurIPS spotlight this year, which showed that localizing the information is not really correlated to editing based on that localized information. And then efficiency, right? Very important. So I covered a little bit of that through unification, but there's also a lot of other kinds of efficiency. So very briefly, I think I'll share the slides anyway, and it's being recorded. But we have a lot of work in our lab on efficiency itself. So some other day I'll give a talk on that. But we've done a lot of work on multimodal adapters, site tuning, multimodal model merging, right? Where can we take existing experts and merge them for new multitask scenarios without having data for the multitask scenario or without having to train again for that multitask scenario. A lot of work on pruning and quantization, right? Sparse MOEs. This is another big area we work on, explainability and model editing. So I was talking about this, right? Does localization inform editing? Actually not. We also have a new iClear submission, which has basically discussed, this one, can sensitive information be deleted from LLMs? Surprisingly hard. We have an attacker and defender kind of system where the attacker keeps trying to extract the private information, the defender keeps trying to delete it. So we bring it down to like 2%, but it's very hard to make it 0. Understanding whether language models have beliefs, right? How to detect those beliefs, update those beliefs. So a lot of work on, all the way to older work on explainability. In fact, evaluating explainability methods and showing that they are not very useful, which I think Danish also strongly works on now. Some new work we've been doing on is language model reasoning agents. This is a very interesting topic to me now. So we had this very exciting paper called Multi-Agent Collaboration, Reconcile Roundtable Conference Improves Reasoning via Consensus Among Diverse LLMs, right? So the buzzword is diverse LLMs. In fact, there was a paper by Google, like Denis Zhu's group, right, that showed how language models cannot really self-reason yet. And this was cited as one of the few examples where going forward, it should be diverse LLMs sort of collaborating with each other. So in this paper, we showed that you can put GPT-4, Claude, Bard 2, and Vicuna and Llama kind of models together. And basically, they try to convince each other to change their answer from incorrect to correct by generating explanations. And at the end of multiple rounds of conversation, even GPT-4 can be increased by 10% by collaborating with supposedly smaller and maybe less capable models. So we have a lot of work on decomposable planning, and this paper shows that weaker models can in fact teach stronger models if done in the right way. I'll probably skip most of this, but if you're interested in language generation and faithfulness, for the last 7-8 years, we've been doing a lot of work on summarization, factuality, faithfulness, most importantly also on metrics for faithfulness. And lastly, if you're interested in NLP plus robotics, I only talked about multimodal, but we also go all the way to actual robotics and robot-based multimodality, where we've done a lot of work on panorama prediction and vision language navigation, but also things like bias and incomplete instruction following for robots. So that's it. Yeah, we are hiring always PhDs and also postdocs. So feel free to get in touch. Thanks.
Questions?
Yeah.
Thank you, sir. That was a nice talk. I have a couple of small questions for you.
Yeah.
So I mean, I'm also new, so I may be wrong somewhere. So these models like VP Gen, VP Eval, for me it seemed like they dependent inherently on structure of English that you are trying to use. That Pikachu is on the table. So if we move to some other language, would we have to create the model from ground up, or could
No.
we?
Yeah, so that's the best part, right? I'll add that to the slides next time. One more advantage of these models is, so I mostly talk about multi-domain, but yeah, same thing applies for multilingual. If you separate the generation part from the planning part, then you basically, so we've shown, like I said, right, we've shown these language model planning capabilities all the way from GPT-4 to something like Vicuna and Llama, right? Closed source versus open source, very big versus very small models. Same thing for the language side. You can basically use a different language LLM to generate the same plans, right? But the best part is the visual grounding stays the same, right? On means the same thing in everyone's world, independent of what language they speak in, right? So all you need to do is change the first module, and then it learns its own prepositions to layout mapping.
Okay. One more I had was the UDOP you had mentioned.
UDOP, yes.
So it seemed that you were trying to edit technical papers and technical PDFs. So would there be a problem, since these are technical papers from different domains, that the model gets something wrong, or is it only for the purpose of editing the text there? The model itself is not generating any text based on what it has.
So the task that it's useful for is not we have done work on actual paper writing, called Paper Robot and others, where you do long text generation, even for technical scientific text, right, which is obviously still a long way to go. But this is not the job of UDOP, right? It's more about, if you see the due benchmark, it's more about document VQA and table entailment and table question answering. So to be very specific questions, about something missing in the table given the rest of the context. Yeah, it will not be able to generate like scientific missing like a paragraph of the text.
Okay, thank you so much.
Hello, I'm Anjanelu. I'm a data scientist at Reliance Jio. So mainly working for Jio cinemas and things like that. So we majorly, like, there are English movies and all there in our databases, but yeah, a lot of lingual, Indian, a lot of various languages, cultures and all. So how do you think these models will work? And if it doesn't work, what is your estimate on how many months it will take, how many people? I mean, just can you give me an estimate of how?
Yeah, so I think it's related to what he just asked, right? So for the part that is using language models as planners, it's basically not going to take that much time. We have tried it, right? It's very convenient to actually be able to take you still have to have a strong enough right model in that language. But if you take the best, say LLM for Hindi, you can still generate images now with Hindi prompts. If you say write like upar instead of on. So that's what I was telling him, right? The best part about this kind of modular approach is that you can actually separate, like, just take in and plug in and plug out different kinds of language LLMs. But for the first part of the talk, which is about unification, that's a little bit of a different answer, right? For something like, Cody, like we built it from scratch. Like it's a collaboration with Microsoft and it's a pretty big model. So there, obviously, you could do it through adapters, right? You could bring in like these different parameter efficient modules and add different language capabilities, but I would not recommend like retraining it from scratch for another language. So to me, the future is definitely like adding more parameter efficient modules and adapters, right? As opposed to like training again from scratch.
If we have budgets, how much RAM, GPU RAM would you think like?
So like I said, it's very different for different papers. Cody is much larger scale, right? In collaboration with Microsoft. Video director, right? The long video generation we did in-house. So that's the advantage in some sense of working sometimes only academically, because you're forced to do it with much fewer GPUs. Like we have much more GPUs than like say 8 A6000, right? But we tried to make sure that the whole long video generation thing can be fit on 4 A100s or 8 A6000s. So that was a big surprise, right? Because even single scene video generation takes hundreds of GPUs. So we did it in a very parameter efficient way. Only the layout modules were updated, and also all the parameters are shared across all the consistent, same color coded bounding boxes.
So in VPGen, we have like these fixed tasks, right? Like counting and layout. So this definitely helps in like the VP well, right? So do you think like if we can add some more controls like bias and all other things, and so then add a reasoning agent on top of it?
Right,
like
same thing there. So that's my philosophy, right? I was trying to say that right now we have good detectors for, not actually that good, but we at least have reasonable detectors for scale and spatial relationships and counting, right? You can imagine even those are not perfect, right? It's still very hard to count objects. So every time in like the next few years, every time you have a better detection module for certain skills, that just becomes a module, right? VP Gen and VP Eval's job is to learn how to create programs over existing modules, not, right? So that's the good thing about separating the two things. There should be an existing library of modules and skills that the whole world contributes to, right? Every time someone has a better counting object detector or another skill detector, we'll keep adding to that. And then the language model just needs to be efficiently like redo some in-context learning to teach it with 3 or 4 examples how to use that new skill. Yeah, so it will be very efficient, just few examples of in-context learning, and okay, now it can use this new skill.
Yep, there are no more questions. Let's thank the speaker once again.
Thanks everyone.